Hello everyone and welcome to my fourth sequential circuit video. In this one we're going to be making a stoplight out of a Moore machine. Or not out of a Moore machine, but it's going to be a Moore circuit. Um, and so we can start off with kinda what we're looking for. And so to start we can go ahead and look at our state diagram. This is the one that I was given. We were told to make another one, but this one does literally the exact same thing that we want our circuit to do. So I figured I'd just use the same one. And so basically, what it is we have this stoplight, and it normally just goes by a timer. So of an arbitrary duration, we control the timer in this circuit. And so when the when the timer flicks up, it changes, and then it'll flick down, and then when it flicks up again, then it'll change again. So from green to yellow to red to green to yellow to red to infinity. However, in this circuit, we can adapt to emergency situations like police cars or firefighters or whatever the case may be. And so we have an emergency switch. And that emergency switch will take any state that we're currently in, and it'll turn the light red. That way, all the cars stop, and the special vehicle can drive through without worrying about a crash. And so to do this, we have three different states, one corresponding to each light state. So green light is going to be 0, 0, yellow light is going to be 0, 1, and a red light is going to be 1, 0. And because we have three different states, we need to use 2 bits in order to represent each state uniquely, which leaves us with one remaining null state of 1, 1, in which case we are going to, we're not going to care about 1, 1. And that's because normally like there are certain circuits where there would be a reasonable probability that both of them would be 1 at the same time, and then you would have to come up with a way to deal with that, whether it be delegating it back to green or whatever the case may be. However, in this case, because the likelihood that there's an emergency signal at the exact same time that the timer switches is incredibly low, we just are going to not care about what happens when that happens. And in the circuit, what ends up happening when you don't care about the switches being 1, 1 at the same time, is that even if the planets align and or the stars align, and it happens, all it's gonna do is just flash for like a millisecond. Whatever, like it'll just go from red to red for a millisecond, or it'll go from yellow to yellow for a millisecond. It'll just like blink, turn off, and then blink back on. So it doesn't really actually do anything. So we don't care about 1, 1 in to make a short story long. And so yeah, that's basically the state diagram. We've been instructed to use a JK flip-flop in this circuit. Ignore this. So that's our transition table that we're going to be using. And then we can go ahead and look at this next state table. So let's see here. Yeah, we can do that after we make the next state table. So in this next state table, I'll go over it relatively briefly. This lab is under the assumption that you know how to make a next state table. But basically, we have green, 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 yellow, 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 and red, red, red. And that's because each state has 2 possible input combinations, or 3 possible input combinations. And like we said, we don't care about 1, 1, so we don't even have to put it in the table. So say the light's green, and both of the timer's off, and there's no emergency, it's just going to stay green. If the timer's up and it's at green, well, it's going to go to yellow. And if the timer is, if it's an emergency, we're going to go straight to red. And so on and so forth down the chart. And to get the J1 and K1, J0, K0 values, all you have to do is, for this one, you just want to look at Q1 in the present state table and what it goes to in the next state table, and then find your J1 based off of our transition table. So in this case, we have QT going to QT plus 1, 0 going to 0. Well, if we look at our transition table, when we have 0 going to 0 and a JK flip-flop transition table, J is just going to be 0. So J is just 0. And we follow that logic all the way down the chart until we fill it out. Lastly, with that information, we can make our Carnot maps, or Carnot, or however you pronounce it. And you do this by just looking at the next state table and say that we want to find the Carnot map for J1. Well, we use the present state bits on our left side, and then our input variables on our on the top or the right side. And then we just read it across. So if we're looking at J1 and say that we're in the state green, because that's what 0, 0 is. 0, 0 is green, 0, 1 is yellow, 1, 1 we don't care, and 1, 1 is red, or 1, 0 is red, rather. So if we want to look at green light when neither thing is active, then we can go to our next state table and say, okay, well, green light, neither one is active, J1 is 0. And so we fill in that chart, and we do that for the rest of all 4 of these diagrams, or these maps, with the special case being, well, since we don't have a state for 1, 1, because on this side it represents the color of the light, well, we just don't care about what the inputs are when we're in a state that doesn't really even exist. And then also, because XE and XT are, like, we're not caring about when they are the same, because that's just an unbelievably unlikely situation, and there aren't really any dire consequences to our circuit. If it does go into this state, there are only very, very minor consequences. Then we also don't care about what goes on here. And what's nice is that when we cannot care about basically half of the table, it makes our equations very easy to write and very, very simple to make circuits out of. So by looking at these Carnot maps, we're able to derive the Boolean equations. So for J1, we have XE or Q0 XT. I'm going to go ahead and assume that you guys already know how to make these if you watched any of my previous videos, so I'm not going to go over that here. But all in all, these are the equations that we ended up getting, and from there we can move on to actually making the circuit. Let me move that over to the side. Let's see here. Alright, yeah, so let's go ahead and look at the circuit. So say that we're at a red light here. That's the current state of our circuit. And our timer is low, and our emergency light is low. So what's going to happen is that on every tick of the clock pulse, well, nothing is going to happen. Because we saw in our next state diagram that if the timer and the emergency light are both 0, nothing happens to our circuit. But say that our timer is active now, well, then it's going to go to green. And it's going to keep going to the next light on every single clock pulse. And this is negatively edge triggered. So And now we can look at the emergency. So right now we're at a green light, and I flick that there because it's negatively edge triggered, so it's not going to do anything. But our timer is low, and our emergency is high, and we're at a green light. This goes up instantly to a red light. And it's going to keep going to a red light because, well, in an emergency, a red light is just going to stay the same. And then say that we're at a yellow light. If I flick the clock again, it's going to go to red. But if it's an emergency, it's also going to go to red. But presumably these things are not synced together. The emergency and the timer, they're completely mutually exclusive. So you have to have two different sort of cues for when yellow goes to red. You can't just use the same cue. Let's see. And then we can kind of go ahead and show what happens when they're both 1. And just to preface, normally this clock would be flashing at like, I don't know, 1,000 times a second. And if we wanted to change the light just once, the timer would go high and back to low in less than 1,000th of a second. So it would only be able to register only one time. And that's why the likelihood that the emergency and the timer being on at the same time is just so unbelievably low. But hypothetically, if it did happen, what would happen? Well, it just turns off for a second. So it'll just flash. But say that it's off and then we turn that off. Well, it just takes another clock pulse and it's just back running again. So maybe it turns off for a second, but it doesn't like break the circuit. It's not like all of a sudden green's going to red and then red's going to yellow. It's really not that bad. So that's the circuit. Oh, and just up here, like all the Boolean equations just turn into circuits. I feel like that's pretty self-explanatory. And so an interesting question is this a Mealy or a Moore machine? We've kind of gone over that in the past videos, but the telltale sign of whether or not something is a Mealy machine or a Moore machine is that you look at the outputs and you see, well, what are the outputs being created out of? And if they're being created with our input variables, xt or xe, or their primes, then it's going to be a Mealy machine because that uses a current input to determine the output. Not entirely, but it's part of the equation. However, Q0 and Q1 are the outputs of previous inputs. And a Moore machine is defined as a circuit in which the current output is defined by previous inputs. Or previous outputs. One of those two. And then the Mealy machine uses the current inputs. So this is a Moore machine, obviously, because we're not using any current inputs. And so another question that is given to me here is when we choose these different flip-flops to use for these machines, we very easily could have used a D flip-flop or a T flip-flop. How does that change the complexity of the circuit? Well, when we use a J-K flip-flop versus a T flip-flop, for example, because J and K are two different variables, they require, because there's going to be J1 and K1 and J0 and K0. So you need to come up with Carnot maps or Boolean equations for every single one of those variables, and then there are different variations of depending on how many bits you have, you could do J0, K0, K or J0, J1, J2, J3. It depends on how many states you have, but typically it's just gonna double the number of equations and circuits you're going to use per project, I guess you could call, or whatever you want to call this whole thing. I guess the big circuit. These are subcircuits, I guess you could say. So it'll double the number of subcircuits that you need to create to get values for all of the different states, or the the J1, K1 values. Because before, we have J0, K0 and T0, T1, but then we also have J1, K1, so it'll double that. And that is all for this video. Thank you for watching, and we'll see you in the next one. Bye-bye.